present the methodology of part of my PhD thesis, that is measuring the brain variability throughout spatial relationships. So what I'd like to do is to introduce another dimension to explain how variable, what are the differences between the human brains using the spatial relationships. So, for example, we have two structures, and in the brain, normally there are studied individually to see what happened with a disease. But what we like to do is to make propose another model to see what happened with the relationship between the structures to explain the variability, and use that for explaining how are the diseases or the genetic differences between the populations in the world. So, for example, in red here we can see two structures, two brain structures from one subject, and those are another one from another subject. And as you can see, maybe there are some variations between this structure to this one, but the relationship between them is the same. So we study that. So what we do, for that we have a data source that is composed by a chain magnetic resonance image, MRI, for us, from healthy subjects. Each one provides a brain image like that, but all the MRI image looks like that. It's a stack of images, and we can reconstruct the 3D body from this kind of image. So, for make the comparison between brains, we have to register. What that means is those are in the same space for making comparisons. In particular, we use the telleric space, that is just the, say that one brain is aligned with another brain. So after that, there could be divided in two groups based in the spacing. The spacing is like these two little cubes. There is what amount of material is captured by each one of the small cubes in this image. So there are two kinds of spacing here. One is in a square, from 1 millimeter to 1 millimeter to another millimeter, and the other one have it's more high. Height. It's 1 millimeter and a half. So that's important for the comparisons and the definition of the relationships. But also we have a 28 labeled structure for each image. So some experts are mark all the images like that in this way. So we can identify clearly what is a structure, or a specific structure in the images. After that, we can reconstruct each one of the structures, like a volume. And after that, we select what are the structures that are important for my study, for our study. For example, here we can see the left lateral ventricle, that is the left convex nucleus, that is the left putamen. This one from here is the left amygdala, and there are other height of these ones. So that we have a set of 28 structures for each image, but for the construction of the spatial relationship, we only take pairs of them. So the process is first collect the data and select the structures for the study. Then we have to select a structure representation. Normally we can take all the structure in consideration for the spatial relationship definition. But in order to in order to make it more fast, the analysis, we can reduce the amount of data and use another representation to make the spatial relationship definition. After that, then, based on the representation, we proposed some spatial relationship definitions, and then we measure the relationship. Then, for each pair of structures, for each subject in the source, we have a set of spatial relationship measurements, and with that we can assess the variability. And the assess of the variability is made with basic statistics for single variables like the media, the standard deviation and variance, only to see what is the dispersion of the data, or use some other statistics like principal component analysis or independent component analysis that is not mentioned here, to take advantage of the orthogonality of the space to see what is the direction of the dispersion of the data. So, for the representation, we use a mass center at single point. Also use the ultimate erosionable point, that it's another procedure. I don't go there with that. Also, we have like a linear representation. This one is a skeleton. So the idea here is that the distance to this line is the same from the boundary of the element. Also, we have used the circumscribed sphere, the described sphere, the surface, or the volume of this brain structure. Then we can define simple spatial relationships like the direction between points or the distance between points. Also, we can take the surface and see the projection from one surface to another to measure the direction one more time. Also, we can use the frequency of distance between points or the distance or the angles between points of each surface to define what is the relationship between them. Then, if we have, for example, this representation, we have only a single volume of distance, for example, for each subject. Then we can apply just basic statistics, like mean and standard deviation, to see what is the variation. But if we have more complex structure for the measure of the spatial relationship, like the histogram of the distance or angles here, we use the PCA, or the principal component analysis, to see what are the directions, the orthogonal directions that represent the dispersion of the data captured for the spatial relationships. And thank you, that's the process. So, another question? Okay.
Registration. What kind of registration did you use and why Telerak?
What's Telerak? Okay,
No,
Telerak.
why Telerak?
Why Telerak? Because I don't do the registration process. It's part of the database that I use. All the images that I take for this analysis were published in a public database that the name is the Internal Brain Instrumentation Repository. And all the images in this space are aligned.
Okay.
And they use the Telerak space. Of course, there are more sophisticated registration space like the ACVM standard that propose not only to be alienated, to be aligned, sorry, and they also manage and propose one way to reduce the variation of the spacing.
And do you know what kind of registration they use?
It's just a lineal.
Really?
Yes. It's a rigid registration, it's a matrix, like an affine registration. Maybe one more.
What software do you use to make all these?
Okay, there are many software for that. For example, for instance, to read the images, I use a library. Its name is ITK, the Insect Toolkit. But many of the open source tools are based in this library. So to see this image, for example, I use a slicer, 3D slicer, that is based in the same library that I use to make my measures. So this is only for visualization, that is one important thing, but for me it's more important to really read and measure the image. So in my process, I don't generate or use any kind of these visualizations, only to explain what is the objective. And for the analysis, I use ITK and also MATLAB. That provides many of the algorithms for that. So ITK and MATLAB, a slicer